Hello, dear listeners of the conference. I'm from Bauman Moscow State Technical University. I'm very pleased to be here. The subject of today's presentation is optimization of curing process of polymer composite materials with epoxy matrix. Polymer composite materials are widely used as structural materials in the manufacture of products in mechanical engineering, aircraft manufacturing, space rocket production, and many other industries. It is known that the quality of the parts made of composites based on thermosetting binders is finally formed during the technological operation curing. A typical two-stage technological process of curing the binder consists of 5 sections. On the first and third, there is an increase in temperature. On the second and fourth, aging, and on the fifth section, cooling. The time and temperature in the second section are determined as a rule experimentally for each particular product. It corresponds to gelation time and temperature. In the technical literature, the study of the temperature field of products in the curing process of epoxy materials only in the solid aggregate state is given. The developers do not take into account the kinetics of changes in thermal properties during heating, which leads to a large error in the study of the temperature state of parts from GFPR during their curing. I will study the curing process of the high-pressure vessel made of carbon fiber, taking into account the phase change of the binders and taking into account their exothermic effects in the curing process. I'm going to examine this topic in the following order. First, the experimental approach. Second, the theoretical approach. In the experimental approach, heat capacity and thermal conductivity of resins were evaluated in the curing process for liquid, gel, and solid state. In the theoretical part, the simulation of curing process was carried out by taking into account the change in the aggregative state of the binder in the process of its curing. The holding temperature at the second section corresponds to the gelation temperature. Experiments to estimate the gelation temperature depending on the heating rate were performed using dynamic mechanical analysis. In the process of curing composite materials based on epoxy binders, the thermophysical properties of the binders vary depending on the curing degree. The heat capacity of the binders, depending on the curing degree, is determined by the differential calorimeter method. It is found that with increasing degree of curing, the heat capacity increases. The thermal conductivity of the binders depending on the curing degree is determined by the laser flash method. The peculiarity of this study is the use of a special crucible, since the liquid binder did not allow withstanding the required dimensions and is transparent to laser radiation. It is found that with increasing curing degree, the thermal conductivity decreases. To study the thermal effect of the chemical reaction during the curing of the binders, the differential scanning calorimeter was used. Using the DSC method, the curve of the thermal effect of the binders was obtained for different heating rates. The genetic parameters of the binders used were determined from the results of the DSC. The obtained genetic parameters will be used to determine the exothermic effects of binders during the curing process. I'll study the curing process of the high-pressure vessel made of carbon fiber. The high-pressure vessel formed with 3 widening zones. Here is shown its size. There is a different thickness in the cross-section of the bottom of the high-pressure vessel. Its thickness varies from 1 and 9 mm to 18 and 1 mm. During the curing of composite materials, the thermophysical and kinetical properties of the binders affect the temperature state of the sample. The ESC PAMA RTM software was used to simulate the curing process. Here is shown the dependence of temperature on time in curing process of the high-pressure vessel at points from 1 to 4. As a point 1 thickness 18 and 1 mm, as a point 2 9 mm, as a point 3 1 and 9 mm, as a point 4 4 and 5 mm. It was found that during curing, uneven heating takes place not only along the bottom control, but also in thickness. The highest temperatures were recorded at point 1, with an increase in the duration of heating. Not only does the temperature increase, but the area of unevenly heated surface also increase. Similarly, the degree of curing changes. It was found that the greater the thickness, the greater the amount of heat released during the curing process. This additional heat flow leads to an increase in the temperature and the degree of curing. It is known that the higher the heating rate, the greater the heat release. It is in good agreement with the results obtained. At point 1, the section of maximum thickness, the heat release intensity also has a maximum value. At points 3 and 4, the thickness is minimal, which leads to the appearance of a low concentration of heat flow. The degree of curing changes in a similar way. The results showed that the maximum amount of heat is released at point 1, the minimal at point 3. So the temperature field along the bottom control varies nonlinearly. The temperature decreases from point 4 to point 3, then the temperature on the surface of the part increases from point 3 to point 1. With an increase in the thickness of the structure due to the concentration of the heat flow, the maximum temperature and the release of heat increases. To ensure a more uniform distribution of temperature fields along the length and thickness of structure, modeling was performed at a lower heating rate, the views of which in first section were 3 K per minute and 1 K per minute in third section. The proposed mode heating leads to an increase in the curing time of 5%, but reduces the temperature gradient in thickness by 8% and in length by 11%. Here is the conclusion. Thanks for listening.